Oh my goodness. Oh my goodness. There's like sunset, this, if you do not get that, we're on the next negatives, but what is this? What is the main round? Here is my how you. Totally nice.
Okay, so that was really an otherworldly experience. As an astronomer, I was there, I was watching this whole event take place, and I knew, intellectually was happening. But, deep in your gut, your reptile brain, just think that the world was in it, right? It was like supernatural, it was unreal. We had a trip of astronomers. We actually brought a large conference of astronomers, about 250 folks, up to Weezer in Idaho to observe that eclipse. And people like broke down in tears. It was really amazing. So today's eclipse is not quite the same kind of eclipse. The eclipse in 2017 is what's called a total eclipse. So that's where the moon's disk completely blocks out the sun's disk. What we're going to have today is called an annular eclipse. An annular eclipse is when the moon's disk almost completely, but not quite blocks out the sun's disk, and leaves a little ring, a ring of fire it's called, around the limb of the moon. This happens not actually all that often. A ring of fire eclipse, an annular eclipse, is relatively rare. Usually, we either have a partial eclipse, which is when the disk of the moon only blocks out part of the sun, but doesn't leave a ring like this, or we have a total eclipse when the moon's disk blocks out the sun completely. An annular eclipse doesn't happen all that often. This is a very striking image from 2012, the annular eclipse that happened back then. It really looks a lot to me. I don't know what this looks like to you, but to me, this looks like the Eye of Sauron. This is what it reminds me of a little bit. Those are any big Lord of the Rings fans here? I have to think there are. Sauron's eye is sort of unfathomably dark. There's this sort of deep, malicious darkness at the center of Sauron's eye. That's not really what we have in the lunar eclipse, in the solar eclipse. So what happens again in a solar eclipse is that the moon's shadow actually passes over the Earth. Like all celestial bodies, the moon casts a shadow into space, and occasionally the shadow of the moon will actually cross over part of the Earth's surface. It doesn't happen all that often because the moon's shadow is quite small, and for other reasons we'll talk about it in a second. If you're inside of the part of the moon's shadow where the sun is completely blocked out, that's a place where you're going to see a total solar eclipse. And if you remember back in 2017, there was something called the path of totality. That was a small region that passed through Idaho, where the moon completely blocked out the disk of the sun. But that path of totality is usually only a few hundred miles, maybe 100 miles across, because again, the moon's shadow is so small. Most folks in the Earth will see instead what's called a partial eclipse. And so the moon's disk blocks out some, but not all of the sun's light for most people. And then a lot of other people will see no eclipse at all. They're completely outside of the moon's shadow. This is an annular eclipse that we're having today. Again, this is a relatively rare kind of eclipse. The reason that we have annular eclipses sometimes and partial eclipses and total eclipses other times has to do with where you are on the surface of the Earth relative to the moon's shadow. It also has to do with where the moon is in its orbit around the Earth. The moon's orbit is not a circle, and so sometimes the moon is farther away from the Earth, sometimes it's a little closer to the Earth. If the moon happens to be closer to the Earth, it has a slightly bigger shadow and is more likely to completely block out. So that's when we're more likely to get a total when the moon is a little closer to the Earth. When the moon is a little farther away, of course, the shadow is a little smaller, the moon's disk is a little smaller, and that's when we're more likely to get an annular solar eclipse. And so when the moon is slightly farther away, we get an annular solar eclipse like what we're going to have this morning. So when we have a total solar eclipse, we have what's called the track of totality. Again, that's where the moon's shadow can, the moon completely occult to the sun. For an annular eclipse, we have what's called the track of annularity. That's places on the surface of the Earth where you'll see that ring of fire. Now, this map shows you the track of angularity of the eclipse, and you can see that it comes close to, but not quite to avoid. We're not quite in the track of angularity of the eclipse. You'd have to get about 4 hours to the southwest of us to get down to the track of angularity. But because we're very close to that angularity, we will still see a almost complete angular eclipse. So the estimate is that it's something like 90% occupancy in estimating voice. But you can see that the track of angularity for this eclipse basically starts out in the Pacific Ocean, crosses through Oregon, then down to Nevada, Utah, New Mexico, and down to Texas. We've been observing solar eclipses for a long time. We're pretty good at predicting them. And in fact, you can go to, there's a link at the bottom here. It might be easier just to Google solar eclipse interactive map, and you can find a map that allows you to interact and figure out what the eclipse will look like at any point on the surface of the Earth today. If you click near Boise, you'll get a little informational window that looks like this. So there's in the table at the bottom of that panel are 3 rows, and they tell you the start of the partial eclipse, when the eclipse will be maximum, so that's when the moon's disk is blocking out as much of the sun's disk as it will from your vantage point. And then the end of the partial eclipse at the bottom. So you can see, of course, today's date, October 14th. Then you look at the times, 15:07. That might be a little confusing for people. So the clock on the map is a 24-hour clock. So 15:07 is 3 p.m. Right? Subtract 12. But then you might say, well, wait, you said there was this morning. I did. This is in universal time. So this is the time it will be in Greenwich, England, when the eclipse starts. So astronomers very often use what's called universal time, so that everyone can have synchronized clocks. But we're not living in Greenwich, England. We're living in Boise, Idaho. So we want to know what time the eclipse is taking place here. And to do that, we subtract a few hours. We're on mountain time. And so the eclipse for us, we start at 9:07. Okay. The darkest part of the eclipse will be about 10:30 this morning. And then the whole thing will wrap up about 11:40. It's almost. So make sense. We're going to track a couple hours from UTC to figure that one out. How do you observe the solar eclipse? I think many of you already know this because you have your eclipse shades. Total solar eclipse, there's a short window of time during the total solar eclipse where it's actually safe to take off your eclipse shades and look at the sun when the sun is completely blocked out by the moon. But for an annular eclipse, that's not true. Okay, you got it? So this is something a 3-year-old can understand. You can never look at the sun with your bare eyes. Famously, scientists throughout the years look at the sun with their bare eyes. It's actually damaged the vision. Famously, Newton stared at the sun for several hours, trying to spot features and surface of the sun, and suffered flipped out with blindness. He's actually blind for a day, suffered really severe headaches for a long time after that. I think his vision never really recovered. So don't feel like that dummy eyes. Use your eclipse shade if you want to look at the sun. And so a 3-year-old can understand this. This is something that I think that most people get. The sun can literally cook your eyeballs if you stare at it for too long. We will today out on the green have a couple of telescopes that we can use to look at the sun. However, those are special telescopes that are designed just for looking at the sun. Okay. Most of the time, most telescopes are not designed to look at the sun, okay? So I don't want folks to go out there and get confused. Oh, they were using telescopes. No, these are special telescopes. If you point your normal telescope designed for looking at stars, if you point that at the sun, it could catch on fire. If you've ever played with a magnifying glass and like set leaves on fire, that's basically what you're doing with the telescope, if you point it at the sun, okay? So you can imagine what would happen if your eyeball back to the telescope. That's if something like that would catch leaves on fire. You don't want to do that to your eyeball. Oh my gosh. So we're going to have a total, an annular solar eclipse today, October 14, 2023. There is another solar eclipse coming up next year in April. You can see the track of our annular solar eclipse in yellow here crossing over the United States. The total solar eclipse on April 8th, 2024. The track of that total solar eclipse you can see in purple or blue. That track actually starts down in Texas and will kind of go up toward the northeast, passing through a lot of states in the Midwest before exiting the United States through Maine. Unfortunately, that total solar eclipse will not be visible from Idaho. You will still be able to see a partial eclipse as part of that from Idaho. But if you want to see the total eclipse in 2024, you're going to need to travel towards the south or at least towards the east. So one question folks often have is, okay, so the moon passes in front of the sun, and that blocks out light, that's an eclipse. Why don't we have an eclipse every month then? We know that the moon like goes around the earth every month. Why don't we have an eclipse every month? That's a really good question. I'm glad you asked it. The reason we don't have an eclipse every month is because the moon's orbit around the earth is tilted. It's tilted. Look at the diagram showing the moon's orbit and how it's tilted around the earth. Most of the time, the moon is either above or below the earth. And so its shadow is cast out into space and not out into the distant figure. So you can see on the right hand, there's an example where the moon is casting shadow during the new moon phase, but that shadow falls above the earth. And then about a month later, the moon is on the other, about half a month later, the moon is on the other side of the earth, and it's casting a shadow, but it's below the sun, below the earth. And so we don't have eclipses every month because most of the time the moon is either above or below the earth. And so we won't cast a shadow. And so in that configuration on the right, the earth is below the moon shadow. On the left, half a year later, the moon shadow is actually, the earth is actually above the moon shadow. And so we only get eclipses when the moon passes through the orbital plane of the earth. And that's what you see at the bottom and the top of this diagram. That is the only time during the year in this diagram where we can have an eclipse, is when the moon is passing through the Earth's orbital plane. The orbital plane of the moon, however, is not static. It doesn't stay fixed in space forever. It actually wobbles around like a coin on its edge. And so the conditions for an eclipse actually will change over the course of the years. And so the moon's orbit actually evolves as the Earth is orbiting around the sun. The moon's orbital motions, all the motions that are involved with the evolution of the moon's orbit have a variety of periodicities, a lot of sort of synchronous events are taking place here. And so there's a cycle of about 18 years for eclipses when the eclipse from one
cycle will match up very closely with an eclipse from that same cycle 18 years later. So this is eclipse cycle of about 18 years. This little chart, it's a little hard to read, but on the bottom, I'm showing you month of the year. And on the top, top to bottom, I'm showing you years. And so those little dots represent different kinds of solar eclipses. And you can see that occasionally there's a good lineup between one solar eclipse and another solar eclipse. And that's that 18-year cycle. Okay. So for example, there was an eclipse back in February of 2008, which has a partner eclipse in the same cycle 18 years later in 2026, like February. See that? How they kind of almost line up, but not quite. Likewise, there was another eclipse in early August 2008, and it has a partner eclipse in mid-August in 2026. And so all solar eclipses are part of these long-term cycles that take place every 18.6 years as a result of the motion of the moon's orbit around the sun. So what about our eclipse today? So here's our eclipse today in October 2023. And so you have to go back 18.6 years to find the last eclipse in this cycle. That was back on October the 3rd, 2005. And so there's this very rich kind of tapestry of eclipses that are kind of linked throughout history. These eclipse cycles take place over the course of hundreds of years. So each time there's an eclipse, you're actually taking part in a celestial event that has this long history going back hundreds of, or even 1,000 years into the past. As I said, astronomers are very good at mapping eclipses and predicting what they look like. And so what do the eclipses in our particular cycle look like through time? So this is an animation showing you where the shadow of the moon was passing over the surface of the Earth during the eclipse cycle of which we're taking part today. And you can see that the eclipse track moves over the surface of the Earth from one eclipse to the next. And that's because the rotation of the Earth is not in any way synchronized to the moon's orbital motion. So the Earth is just rotating underneath the moon, and occasionally the moon's shadow will pass over the Earth, and very often it passes over a different part of the Earth from one eclipse to the next. So the last eclipse in the current cycle of eclipses is this one. This is that one I just showed you, 2005, October 3rd. The track of the moon's shadow in this case passed through kind of north central Africa. What was happening back in 2005? Anyone remember? Those of us who are old enough to be there may not quite remember it. Well, in August of that year, 2005, the Mars Reconnaissance Orbiter was launched from Cape Canaveral. The Mars Reconnaissance Orbiter is this enormous spacecraft with a giant camera. You can just see the giant camera down here on the bottom. This camera is called the high-rise camera. It's actually designed to monitor and observe the surface of Mars with very, very high resolution. You can almost read a newspaper on the surface of Mars from this telescope in orbit around Mars. It has exquisite precision and resolution. In fact, the high-rise camera on board the Mars Reconnaissance Orbiter took this picture. Anyone recognize this picture? A little weird looking. This is really an amazing achievement in space science and engineering. What you're seeing there is a picture of the Mars 2020 rover landing on the surface of Mars, photographed by the Mars high-rise camera. You can see the parachute, and underneath the parachute, that's the Mars 2020 rover that's now on the surface of Mars. So they actually caught this landing. This is the first time that had ever been done. And it was largely due thanks to the enormous ingenuity and effort by NASA scientists and engineers to take a picture like this. The high-rise camera was approximately 430 miles from the Perseverance rover and traveling at about 6,000 miles per hour when this image was taken. So you can imagine trying to take a picture from like a moving train. We'll make that train move, about 100 times faster, 1,000 times faster, and try to imagine taking a picture of something falling through the sky at the same time. That's basically what happened here. It's practically a miracle of science. Another eclipse in this cycle took place back in 1789 May 24. That was a good year. Anyone remember that one? It's a good year, 1789. The eclipse track for this one actually passed over the middle of the Pacific Ocean. It's possible that Polynesian peoples who inhabited the Pacific Ocean were able to see this eclipse. It was quite a short eclipse, but it still passed over their heads. Polynesian astronomers were very accomplished. One of the key things that Polynesian astronomers did was to help their people navigate the oceans. As you can imagine, out in the middle of the Pacific Ocean, there's not a lot of land features to navigate by. And so Polynesian sailors got very adept at reading the skies, reading the waters, reading the winds, to understand how to migrate from one island to the next, thousands of miles apart. So it's very possible that they observed this eclipse, and it was probably very striking for them. Folks out west, however, maybe they were not paying attention so much. 1789 was the year of the first meeting of a few hundred years of the Estates General in Paris. Anyone remember the Estates General meeting in 1789? What happened at the Estates General meeting in 1789? This is the beginning of the French Revolution. This is the beginning of the French Revolution, the first French Revolution. The States General was convened by King Louis XVI in January of 1789 to address the calamitous French national budget. As you may recall, things did not go so well for King Louis XVI. And so maybe it's just as well that this eclipse kind of skipped Europe. They were a little busy at the time. Probably wouldn't have noticed. And so this cycle of eclipses has been ticking along throughout human history, kind of this sort of steady metronome punctuating human history, going back hundreds, even thousands of years for each eclipse. This cycle has the name Saros. It's called the Saros cycle. It was named actually by Edmund Halley of Halley's Comet fame back in the 1600s, who noticed this cycle. It was a cycle that had been noticed going back for a long time, but it hadn't been named in the Western world until Edmund Halley came along. But as I said, astronomers have been observing these eclipses hundreds, thousands of years into the past. And one of the most accomplished group of astronomers long in the past were the Babylonian astronomers. Babylonian astronomers going back to the 2000s BC at least, their astronomy system is really the basis for our modern astronomical system. They named many of the constellations that we use today, and they helped us to establish some of these very long cycles in the sky that we even still use today. This is actually a cuneiform tablet describing observations of Halley's Comet back in 164 BC. In fact, the very first recorded writer in human history was a Babylonian astronomer. This is a figure showing her. She was a Babylonian astronomer and priestess, Enheduanna. Forgive me if any Babylonian speakers in the audience. She was actually appointed an astronomical priestess by her father, who was the king. And she was a very accomplished observer, but also an accomplished writer. She wrote some of the standard poetry in Babylonian literature, and her poetry was actually used as the basis for Babylonian literature going forward hundreds of years into the future. So I thought it'd be fun. Let me just read you one of her poems. She worshipped the moon, and so she wrote a very lovely poem describing her love of the moon. Lady of all the divine powers, resplendent light, righteous woman clothed in radiance, mistress of heaven with the great pectoral jewels, who loves the good headdresses befitting the office of a priestess, who has seized all seven of its divine powers. My lady, you are the guardian of the divine powers. You have taken up the divine powers, you have hung the divine powers from your hand, and you have gathered up the divine powers and clasped the divine powers to your breast. Like a dragon, you have deposited venom on the foreign lands. When you roar at the earth, no vegetation can stand up to you. As a flood descending upon these foreign lands, powerful one of heaven and earth, you are their Inanna. That's the name for the goddess of the moon, Inanna. So Babylonian astronomers observed many eclipses that passed through their lands, and they got very good at actually predicting the occurrence of eclipses. And so when you go out this morning to observe this annular solar eclipse, remember this long history that you're taking a part in. You're taking a part in a ritual, a human ritual going back thousands and thousands of years, going all the way back at least to the Babylonian astronomers, Polynesian astronomers, maybe a couple of precocious tweens as well will take part. And sort of the miracle of modern science, which is really enabling these detailed and accurate predictions that we're going to enjoy this morning. So as you go out this morning, I want you to think about not really Sauron's eye, not this sort of ring of fire filled with dark malevolence. That darkness is not empty, but full. It's full of this rich history of human experience, this long cycle of punctuating celestial events going back thousands and thousands of years. And with that, I will stop and take any questions. Thank you very much. Maybe folks can give us a light in the audience. We've got some runners here who have the microphones. Who have questions, we're happy to take it. Everyone's just super eager to get out of the time, right? Yeah. I'll tell you what, if you want to ask questions, I'll hang out at the front here. You can come down to the front. Everyone else, you can head out and we can help you. We've got arrows pointing the way. Enjoy your